All right, this is Wednesday, January 13th, 2021. You students had a homework assignment that you turned in called Coulomb's Law, and I'm just going to debrief you a little bit about the answers to it. So it begins, first you have to understand that Coulomb's Law equation says it's the product of Boltzmann's constant lowercase k times charge q1 times charge q2 divided by the distance between those two charges squared. When we ask for relative effects, you don't have to plug numbers in for each value. If I said, what happens if I double the value of Q1? You don't have to ask me, well, what was the original value of Q2? Because that's not going to matter for the question I'm asking. So for number one, they ask, what happens to the force between two charges if the distance between them is tripled? Well, R is the distance between them, and it's in the denominator, and it's a squared quantity. So if I replace the original unknown distance r, whatever it is, 1 meter, 1 centimeter, 1 kilometer, doesn't matter. If I replace that with 3 times the distance inside parentheses and then square it, what I get is 1 divided by 3 squared, which is 9, times the original distance, whatever it was. And so to answer the question, what happens to the force between two charges if the distance between them is tripled? The answer is it becomes 1/9 as strong as the original charge, whatever value that might have been. And that's how you do all 7 of these that are on the front side of this handout. For number 2, if you quadruple the distance, then it's 1/4 squared, which is 1/16 of the original force. For number 3, if I cut the distance in half, then that is 1/1/2 r squared. I know how you love math. So that is 1/1/4 times the original force. And 1/1/4 is 4. So this becomes 4 times the original force. For number 4, it asks, what happens to the force if the magnitude of one charge is doubled? Well, then it's going to become twice the force of the original situation. Number 5, what happens if both charges are doubled? Well, then it becomes 2q1 times 2q2, and 2 times 2 is 4. So this becomes 4 times the original force. For number 6, if I double both charges and double the distance between them, doubling both charges we've just seen is 2 times 2 on the top, and doubling the distance between them is 2 squared in the denominator. This becomes 4 divided by 4, so the force remains the same as the original value. And finally, number 7, what happens if the magnitude is doubled for both and the distance is cut in half? So that becomes 2 times 2 divided by 1/2 squared times the original force. 2 times 2 is 4. 1/2 times 1/2 is 1/4. 1/1/4 is 4. This becomes 4 times 4, and the answer is 16 times the original force. Now let's flip to the back side, page 2 of 2, where you had 10 problems to solve. Most of you did pretty well. Number 1, 2 particles each with a charge of 1 coulomb are separated by distance 1 meter. What is the force between the particles? Well, F equals K Q1 Q2 over R squared. And in number 1, Q1 is 1, Q2 is 1, R is 1. 1 times 1 divided by 1 squared is 1. So the answer becomes it's just K. In other words, 8.99 times 10 to the 9th power newtons, because the meter squared and the coulomb squared will have canceled out. So 8.99, or as used in this handout, 9.0, or even just 9, times 10 to the ninth power newtons. There's the answer for the force for number 1. For number 2, what is the force between a 3 Coulomb charge and a 2 Coulomb charge separated by the distance of 5 meters? So K times 3 coulombs times 2 coulombs divided by 5 meters, quantity squared. You get 2.16 times 10 to the ninth power newtons. I like having you practice using the Greek prefixes if you can. 10 to the ninth power is called a giga. Gigabyte is billions of bytes. 10 to the ninth is a billion. So you could call this 2.16 giganewtons as the amount of repulsion between these two charges, because they're both positive charges, like charges repel. And by the way, the handout only lists values to 1 sig fig in general, but I'm asking you to override that and display and calculate your values to 3 sig figs for this homework. And in general, please do that unless I say, estimate this. Estimate is a free pass to perhaps just do order of magnitude or 1 sig fig. Number 3, calculate the force between a 0.006 Coulomb charge and a 0.001 Coulomb charge 4 meters apart. K times 0.006 coulombs times 0.001 coulombs divided by 4 meters, quantity squared. You get 3,380 newtons. And if you disagree on the last digit, you say, oh, it rounded down to 3370 because it was 3375 almost or just over. That's tolerable. You can round off at the very end when you write down your final answer, or more properly, you can round off each step of the way, in which case your answer might be slightly different out in the third digit. That is not something that is inexcusable. That is something that is understandable and tolerable and acceptable. Okay, number 4, calculate the force between this charge and that charge. Well, K times 0.05 coulombs times 0.03 coulombs divided by the distance in number 4 is 2 meters. Some of this you can do in your head, like 2 squared is 4. But in general, you use your calculator, and I get 3.37 times 10 to the 6th power newtons. Again, there's a Greek prefix that represents 10 to the 6th power. It's called mega. 3.37 mega newtons. Capital M means mega. Lowercase m means milli. Very, very different. They're different by a factor of a billion. Number 5, 2 particles are each given a charge of 5 times 10 to the negative 5th coulombs. What is the force between them if the distance is 2 meters? So K, and since each one is 5 times 10 to the negative 5th coulombs, that's really a number that you can go ahead and just squared on your calculator, Q1 times Q2. So that value squared, and the distance again, 2 meters, quantity squared, I get 5.63 newtons. And it is a repulsive force because they're both the same sign. Number 6, the force between a pair of charges is 100 newtons. The distance is given. If one charge is this value, what's the strength of the other charge? So you have to do a little bit of algebra first. If F is equal to K times Q1 times Q2 divided by R squared, and the only thing you don't know is Q2, then you have to rearrange this equation to solve for Q2. Begin by multiplying both sides by R squared. R squared times F on the left is equal to K, Q1, Q2 on the right. Now divide both sides by k. Divide both sides by q1. You have q2 is equal to r squared f divided by k divided by q1. And when you get done putting that into your calculator, it works out to be 0.0005. Now here's a thing. You students seem to think that the zeros count as sig figs, but they're just placeholders. Right now, I've only listed this to one sig fig. So where's the second digit? Where's the third digit? Coulombs. Well, there's a Greek prefix that means 10 to the minus 3. It is milli. And if I go 1, 2, 3 to the right, I could say the answer is 5.56 millicoulombs. Okay, these both say exactly the same thing, but one is practicing your skill in using the Greek prefixes to express the answer. These two are saying exactly the same thing. One is using your skill in using the Greek prefixes to express the answer. These two are saying exactly the same thing. But please practice these Greek prefixes, particularly if you want to go in a technical field. Number 7. Two equal charges are separated by 1 meter. They experience a repulsive force of 1,000 newtons. So what's the strength in coulombs of each charge? They're identical charges, which is important. So F equals K Q1 times Q1 again, because they're identical. If they're identical, I could substitute Q1 for Q2 divided by R squared. Now it's Q1 that is unknown. And again, I've replaced Q2 with Q1 because it said Q1 is identical to Q2. So I'm doing substitution. I have to rearrange this equation to solve for Q1. Multiply both sides by R squared again. R squared times F is equal to K times Q1 squared. Divide both sides by K, then take the square root. Q1 is the square root of R squared F, and yes, you could pull the R squared out from the radical sign if you wanted to, divided by K. In fact, you should. You should simplify these things and call it R radical F over K. When you get done using it on your calculator, it'll say, 3.33 times 10 to the negative fourth coulombs. It's surprising how many of you left off the units. It's like one of you didn't leave the units on, and then the rest of you just did whatever that person did, which implies that there's much more background communication going on between you students than there should be. Now, there is no Greek prefix that means 10 to the negative fourth, but there is one that means 10 to the negative 3. So I can move the decimal point to the left one place and say this is 0.333 millicoulombs. There's also a Greek prefix that means 10 to the negative 6th power. And that means I can move my decimal point 2 places to the right and list this as 333 microcoulombs as the answer for number 7. Number 8, the force between a pair of 0.001 charges is 200 newtons. What is the distance between them? So once again, we start with Coulomb's law. They're telling us that each charge has identical value, and they're asking us to solve for the distance between them. So once again, we have to do a little bit of algebra and isolate r all by itself. First step, multiply both sides by r squared. Second step, divide both sides by the force. Last step, take the square root of both sides to solve for r. So r is going to be the square root of K, and since the two charges are identical, I could again substitute and say this is Q1 squared, and then pull it out from underneath the radical as I had with the previous problem with F down below. So pulling that out just because I can, I have R is equal to Q times the square root of Boltzmann's constant divided by the force. So each charge, both Q1 and Q2, oh man, I'm sorry, I wrote the wrong variable there. R, the resulting distance between this pair of 0.001 Coulomb charges, for which the force is 200 newtons, works out to 6.70 meters, is the value of R. Number 9. The force between two charges is 1,000 newtons. One charge has this value. What is the other has that value? And again, what is the distance between them? I'll just get to the answer. The answer is R is equal to 0.030 meters. Now, there is a Greek prefix that means 10 to the minus second power. That Greek prefix is called centi. So I could say that this is 3.0 centimeters, and that is identical to saying it's 0.030 meters. Number 10, the force between two charges is 2 newtons. The distance is given. If one of the charges is this, what is the strength of the other charge? Now, strength can mean magnitude, although I would have preferred that you actually include the algebraic sign. And it's not clear. It says the force between them is 2 newtons. It doesn't say -2. So presumably it is a repulsive force. And if the first charge is positive, then the second charge must be positive as well. I don't know if I should bother doing this, but you're solving for Q2. F is equal to K Q1 Q2 over R squared. So Q2 is equal to R squared F divided by K divided by Q1. And we get a value of 3 times 10 to the negative 12th power coulombs. And I'm just leaving this one at 1 sig fig for here because it's time to end this debrief.